So we learn length and we learn path. Another definition that we have is the degree. So the degree of a given node is the number of children that that node has. So the leaf degree is 0, doesn't have any children. And I guess the height of the tree also is important for us. We're going to use the definition of the height of the tree, and that's the number of edges on the longest path between a node and a leaf. So here, in both of these pictures, the level is 2, and the longest path is also 2, right? Because everywhere we go, we have to go through 2 basically edges to get to the leaves. And that means the level of, or the height of this tree is 2. Like, so the height and the level are pretty much the same, but the levels are, we're going to count them from level 0, 1, 2, 3, but the height of the tree is going to be the longest level basically that we have in a tree. So I guess, we already talked about subtree. So we have a left subtree, a right subtree if we only have, 2 children. But the tree not necessarily going to have only two children. Each node can have, 0 to many children. And that's how the tree structure it is. But we're talking about binary tree specifically, that telling us that the degree of this tree is always going to be 2 maximum. It means that each node only going to get maximum 2 children. And that's what we call it binary tree. So it's not only going to be tree that has a root and leaves and all of those things, but also each node, the maximum children that they can have, it's going to be only 2. So that's why it's easy to say left child, right child, because we only have 2. So one of them can be considered the left one, and the other can be considered the right one. So these are some definitions here as well, specifically about the binary tree and the terms that we use inside the binary tree. So like a definition of the leaf or the length, they're the same. The depth of, or another thing, the depth of a node in a tree is going to be the length of the path from the root to that node. So basically I have to see how, which level is that node is, and that's considered the depth of it. How depth we have to go inside this tree to find that particular root. And we're always going to start from the root no matter what. So that's why it's going to be the length of that from the root. We already talked about the level, and we already talked about the height. So, if the tree is empty, the height of the tree is -1. But when immediately been added the 0, the root's going to be inside, and that's the only thing we have inside the tree. The height of the tree is going to be considered the 0. Siblings, I already said, they have the same father. So here's some of those examples on the picture, right? So you have the root, you have the left child of the root, you have the edge that, from the root, you have an edge to the left and right children. And then each children, they can have their own subtree. So you show the subtrees with the blue. It can be even more, right? So you don't have, you're necessarily not going to have a tree that are going to have exactly same levels, right? So, you may have in the left side, you can go all the way to the level 10, and on the right side, you can go all the way to level 5 only maximum. So the height of the tree is 10, but they're not all, we don't have all the possible nodes in that level, right? So the level can be empty. So an example that you can see here, for example, in the picture A, if you look at this, first of all, you can tell that this is a binary tree now, like our root has 2 children. And when we get to the last level, they're all full, right? So we usually also just by default, we always start from left to the right. So you see the level all the children in the last level, which is level 2, is going to be 45. So it's starting from left. 45, 57, 67, and 107. So all of them are full. Same thing in level 1. We only can maximum have 2 children in this level, and they're all full. So 55 and 100, they're going to be always count or start from left in each level. And then 60 is the only one you can have. So as you can see, you can easily calculate how many nodes we can have maximum in a particular level of your tree. So as I said, minimum number of nodes in the level 0 is going to be either 0, right? You don't have anything, empty, completely empty. You only have 1, which is the root, the maximum number of nodes you can have. Maximum number of nodes you can have in level 2 is 4, right? 0, 1, 2, 3, 4. So this can be easily calculated. So you can have a formula to calculate it, and there is a formula for it to calculate exactly how many nodes we're going to have in each level of a tree. Look at this one, the B. So we have G in level basically 0. In level 1, we have F and R, the maximum number of the nodes we can have. But then we get to the last level, we only have 3, but we could maximum have 4, right? So we're missing a child, and obviously that child is a child of an F, right? So basically the father is going to be the letter F. So and also we talk about levels and the height of the tree and so on and so forth. Now we're going to specifically talk about the binary search tree. So binary search tree is going to be a specific type of binary tree. So it is tree, it is binary, I mean you only can have 2 children maximum for each node. But also it has other properties, and those properties has to be maintained. If you don't maintain those properties, then that particular binary tree then no longer is going to be the binary search tree. So the very first important property of the binary search tree is that we're not going to accept any duplicates. So it's going to be used as a set, right? So set data structure, we don't have duplications in it, so we don't accept duplication. Another very important property of a binary search tree is that for every single node in the tree, the value of any node in the left subtree is going to be the less than the value of the node itself, and the value of any node in the right subtree is going to be greater than the value of the node itself. So basically, if you just think about the root itself, the left child of the root is going to be less than the root, and the right child of the root is going to be the bigger than the root value itself. And that has to be correct for every single node you have inside the tree. So when you building your tree, that means you're adding element one by one to your tree, you have to make sure you're maintaining these 2 important properties. So again, it's data structure. We use that to so that's why you see it's using a particular order in order to add elements. So you have to maintain that order. And so anytime we're adding elements, so like any data structure, like linked list and array list or any type of data structure we discuss, we always want to add elements into them, remove elements from them, and also search. Or maybe even print them out, right? So the binary tree, as binary search tree, also the same thing. It's a data structure, so we should be able to add element into it, remove the element from it, be able to print all of the elements or that are already there, so print them out, or traversing basically all the elements that we stored in it, and also be able to search for a particular key. So but as we're doing all of these, what is very important is we're going to keep it as a binary search tree, because if you don't, if you just randomly do these things or not have a systematic way when you're adding element or removing them, then the structure is going to be broke. And when this structure broke, there's no that structure no longer is a binary search tree, so you cannot apply any of the rules of the binary search tree to it anymore. So the two very important properties of a binary search tree: no duplication, and always the children in the left are less than the node, and the children on the right are going to be bigger than their node itself. So in order to represent this in a Java program, for example, we're going to use again some concept that we had in the linked list, right? So in the linked list, you had nodes, and you connecting the nodes using the the reference to the next node and stuff like that. Here, we're also going to node, but these nodes are a little bit different from the nodes that we had in the linked list data structure. These nodes, we call them tree nodes. So the tree node is not only going to store the element of the node, but also is going to store the reference to the left child and the right child, right? So each node needs to know who are the children's. So we're going to use those as a reference. So basically, we're really using the linked list data structure to represent the tree, right? The binary search tree. So we're going to implement this as well. We're going to implement all of the methods that we did exactly, inside the linked list array list. So we're going to implement our own binary search tree, which pretty much going to be similar to what you see on the slides. But as we're implementing, we're going to discuss about it. We're going to analyze it. So that's the important part of it. So I'm going to stop here, and now that we know all the definition of it, only thing I'm going to just kind of do that is going back to the very first two examples that we had here, and just kind of try to see if there are binary search trees or not. So look at the first one. Is it a binary search tree? I have to see. We're starting from the roots, and we're looking at the children. Left child should be smaller than the root. It is. 55 is less than 60. And right child should be bigger. So 100 is bigger than 60. So we're good. Now we go to the 55. We're looking at the left is smaller. We're going to the right is bigger. So we're good. So that means that this is so far is a binary search tree. Now we're going to 100. Left should be smaller, which is true, and right should be bigger, which is also true. So that also correct. So and we don't have any duplication. So this is a binary search tree indeed. And now let's look at the other one. So G and F. So F is smaller than G, right? So this is correct. And then we're going to the next one. G and then R. So R is bigger than G, right? So that means that's also correct. And so now we have to go to the F and then look at the left side of the F. So A is bigger than F, obviously, right? So that is not a binary search tree. So everything in the left should be smaller. And so if you really want to think about it in order, then A is bigger. So that's not a binary search tree. So we're going to stop here. And so at least you know that's chapter 25 of Dr. Liang book. So you can review that, and then we'll come back and we're going to start, again, as I said, we're going to start coding it. So that is going to be part of our assignments as well for the next week after we're done implementing the binary search tree. Okay, talk to you guys later again. Bye.